Introduction to one's complement. Understanding sign number representation in binary. Hello, everyone. Welcome to today's lecture on one's complement. Uh, this method is important for understanding how computers represent sign numbers in binary form. Binary number system recap. To start, let's briefly recap the binary number system. Binary numbers use only two symbols, 0 and 1, to represent values. And this system is fundamental in computing because it aligns with the on-off states of digital circuits. So for example, the decimal number 5 is represented as 0101 in binary, and the decimal number 3 is represented as 0011. Understanding this basic concept is essential before diving into sign number representation. And if we look at this Python code, this code snippet converts decimal numbers to their binary equivalents. So we have this bin function, and this bin function is used to convert a decimal number to a binary string prefixed with 0b. So decimal 5 and decimal 3 are the decimal numbers 5 and 3, and binary 5 and binary 3 are their binary representations, 0b101 and 0b11 respectively. Sign number representation. In computing, we need a way to represent both positive and negative integers. One early method developed for this purpose is called one's complement. Unlike unsigned numbers, which can only represent positive values, signed numbers include a mechanism to indicate both positive and negative values. And one's complement is one of these mechanisms, and it's a stepping stone to more advanced methods used today. And if we look at this Python code, we have this function called decimal to binary, and decimal to binary converts a decimal number to a binary string without the 01 prefix, and it uses a bin function and replaces 0b with empty string to remove the prefix. One's complement explained. So one's complement is quite straightforward. In order to find the one's complement of a binary number, you simply invert all the bits and change all zeros to ones and all ones to zeros. So for example, the positive binary number 0101, which represents 5 in decimal, becomes 1010 in one's complement. And this new binary number represents -5 in the one's complement system. And let's take a look at Python code. We have a Python function called one's complement, and this one's complement function inverts all bits of a given binary string. How does this do that? It uses a list comprehension to iterate over each bit, changing 0 to 1 and 1 to 0. And before using this, we have positive binary variable, which is the binary representation of 5. And by calling one's complement, and passing positive binary as a parameter, we're computing the ones complement of 0, 1, 0, 1 as 1, 0, 1, 0 and prints it. Converting between positive and negative numbers. Let's walk through the process of converting a positive binary number to its negative equivalent using ones complement. First, write down the binary representation of the number. For instance, the number 7 in binary is 0, 1, 1, 1. Next, you want to invert all the bits. Then 0, 1, 1, 1 becomes 1, 0, 0, 0. So this binary number 1, 0, 0, 0 is the ones complement representation of -7. Let's take a look at Python code. And we have Python code that converts a positive decimal number to binary and then finds its ones complement. So we looked at decimal to binary. I guess one thing to keep in mind is this zfill part. We are doing this to ensure a 4-bit binary representation, and ones complement function computes this ones complement. Addition and subtraction using ones complement. So arithmetic in ones complement involves some unique steps, particularly with addition. So when adding two numbers, you perform binary addition as usual. If the sum produces an end around carry, this carry must be added back to the results. This might not make sense, so let's take a look at two examples. First example adds 5, which is 0, 1, 0, 1 in binary, and -5, which is 1, 0, 1, 0 in binary. Then the sum is 1, 1, 1, 1, which represents 0 in ones complement with no carry. Second, let's look at 3, which is 0, 0, 1, 1 in binary, and -2, which is 1, 1, 0, 1. If you add these, you will have the initial sum as 1, 0, 0, 0, 0. We can see that we have an end around carry 1 here. So you want to add this carry back, which gives us 0, 0, 0, 1, which is 1 in decimal. And let's take a look at this Python code. We have add binary function, which accepts two parameters, bin1 and bin2. So this function adds two binary numbers and handles end around carry. So the first thing it needs to do is calculate max length so that we can use the max length to ensure that both binary strings are of equal length using zfill. And then the sum is calculated by converting binary strings to integers, adding them, and then converting back to binary. And we have this logic here. If the result exceeds the original bit length, it's going to add the end around carry here. We're adding 1 here. Advantages and disadvantages of ones complement. So ones complement has both advantages and disadvantages. On the plus side, It is simple to implement and easy to understand. However, it has significant drawbacks. One major issue is that one's complement has two representations of zero. It has positive zero, and which is 0, 0, 0, negative zero, which is 1, 1, 1, 1. And this dual representation can cause confusion and error. Also, arithmetic operations, especially addition, as you've seen in previous slides, are more complex due to the need to handle the end around carry. Practical applications and historical context. So historically, one's complement was used in some of the earliest computers. For examples, the UNIVAC 1, one of the first commercial computers, you can see in this image, used one's complement arithmetic. While modern systems have largely moved to more efficient methods like two's complement, it is important to understand one's complement because it gives us valuable insights into the evolution of computer arithmetic and the challenges early computer scientists faced. Comparison with other representations. In order to appreciate one's complement fully, it is helpful to compare it with other methods of signed number representations. Two's complement, for instance, does not have an end around carry and has only one representation of zero, making arithmetic operations simpler. On the other hand, the sign magnitude representation uses a separate sign bit to indicate positivity or negativity, but like one's complement, also has two zero representations. So each method has its pros and cons, but two's complement has become the standard due to its simplicity and efficiency. And here, if you look at Python code, here's an example of two's complement function. And this two's complement function calculates the two's complement of a binary number. So we pass binary string, and what it first does is it first finds the one's complement of the binary string, and then it adds a one to the one's complement and ensure the result has the same bit length by calling zfill with n. So, for example, if you have positive binary 0101, which is a binary for 5, the one's complement is 1010, and adding 1 gives 1011, which is -5 in two's complement. Conclusion. So in summary, one's complement is an early method for representing signed numbers in binary. We've looked at its mechanics, advantages and disadvantages, as well as its historical significance. Comparing it to other methods, we see why it was eventually superseded by two's complement. So understanding one's complement is important in understanding the evolution of binary arithmetics in computing. Thank you everyone for listening.